So we're going to talk about work when the force is not constant. But before we do, let's just quickly review what positive and negative work is. So we know that work is when you transfer energy to or from an object by a force that's acting on the object. And we know that positive work occurs when the force that does the work is in the same direction as the displacement. And negative work is when the force doing the work acts opposite the direction of the displacement. So let's take a look at lifting a box. When we lift a box, the box goes up into the air, and the force of gravity is opposite the displacement. So that work is actually negative. So we could say that that work turns into a negative potential energy. Now, the force that's due to the push, that is positive work because it's in the direction of the displacement. Now, in the case of a dropped block, now the displacement is down, and that's in the same direction as the force of gravity. So that conservative force that we defined before is going to take that work and turn it into kinetic energy. We defined the constant or average force multiplied by the displacement as the work done. But we never really talked exactly about this idea of multiplication. When we multiply two vectors that are perpendicular to each other, we call those cross products. But in that case, no work is being done because we defined work as the force parallel to the displacement. Well, this dot right here tells us the parallel part. This dot is, I should have vectors on here, force and displacement. When we do the dot product, that is telling us the force that is in the same direction as the displacement. So a dot product is the multiplication of two vectors that are parallel to one another. So we're doing the dot product, not the cross product. We'll get into cross products when we deal with torque later on. So there's a system that's set up with something called the right-hand rule, where we take our fingers in this orientation and our thumb points in what's called the I-hat direction. Up is the J-hat direction, and K-hat is coming out on this z-axis. When we multiply two vectors that are in the same direction, I-hat dot I-hat, we get 1. So these are called unit vectors. But if we multiply as a dot product two vectors that are at 90 degrees to each other, whether it's I-hat dot J-hat or I-hat dot K-hat, those vectors are 0. So that would be like saying the work done of two vectors that are perpendicular to each other, that would be 0. Well, what happens when the vectors aren't perfectly parallel to each other? So let's take a situation like this. We have A multiplied by B, but it's only the component of A that is parallel to B. So if we say A I-hat, in other words, A that's parallel to B, so these two I-hat directions, that would just be the multiplication of A times B. So 4 newtons and 2 meters, 4 times 2, that would be 8. Now, if we have two dot products, how are we getting this A? Well, this A is the component, the adjacent side of this triangle, and that would be A cosine phi times B, or we can just pull this B out and say AB cos phi. So sometimes the formula for work written as a dot product is also written as Fx times cosine phi to find that parallel amount, which is the dot product. We know that the area of a rectangle is equal to the multiplication of the two sides. So if we have a rectangle which is made up like a graph, and we have a constant force F and a position that it ends up traveling, x, then we know that F dot x, the forces that are parallel to each other, are going to equal the area under that graph. Well, what happens if that function is changing? Well, in that case, we have some function f of x, and what we're doing is we are summing up all of the little derivatives of x, dx, and we're summing them up all the way underneath that function. So what is that area? That's the integral. The work is the integral from x naught to x final of that function f with respect to position. So this formula works for a changing force, where our formula before had to only solve problems when we had an average force or a constant force. To get more comfortable with the integral of force with respect to displacement, we can do some derivations using integration. So let's find out the work to accelerate an object. And if we say that work is equal to the integral of f dx, if we're dealing with the force to accelerate, we know that has to be a net force. And we know that F net equals ma, and that the mass would be constant. So we can pull that out of our integral sign. And our acceleration would be a, and this would be dx. We know that we would be doing this from x naught to x final. But we know that the acceleration at any moment in time is dv dt. So we can integrate that dv dt, and we also have dx. But there's a problem here because we're integrating with respect to all of these different derivatives. So what we can do is do a little sidestep over here where we say the acceleration is equal to dv over dt. And then using the chain rule, we can split this up and say dv over dt, and then we can put anything we want in here that would cancel each other out. So if we put dx's in here, we can see that these two would cancel and we still have dv over dt. But what's nice is that we know that dx over dt is our instantaneous velocity. So we can say dv over dx is equal to v, or multiplied by v, because that dx dt is our v. So we can rewrite this as v dv over dx. So dv over dt is equal to v dv over dx. So let's just sub that in. So for this, we're going to sub in this. So that becomes m over v dv over dx times dx. So these dx's will cancel, and we're left with w is equal to m, the integral of v dv. Well, what are our bounds now? Now we're integrating with respect to velocity, so we're going to do this from initial velocity to final velocity. And doing the integral of v dv, we know that that is 1/2 v squared, and we can say 1/2 mv squared from 0 to v, or, well, we can say v naught to v final. That's going to equal 1/2 m v final squared minus 1/2 v mv initial squared, or we can say that work is equal to the change in kinetic energy. So we're going to do another integration and do this as a derivation, and these are a really good way to get a handle on understanding how work is related to a changing force. So let's do this for working to lift. And let's say we have W is equal to F dx to start with. Well, what's the work to lift an object? That would be the force of gravity. That's the force needed to lift an object at a constant velocity. Well, we know that's mg, and both m and g are constants, so we can pull that out and say mg, the integral, and what's the x position for lifting something? Well, that would be dh, or the height. And so we can lift it from height initial to height final. And we know that the integral of dh would be h. So we would have mgh from h initial to h final, or mgh final minus mgh initial. Well, what is that? What is that work? That is going to be mg, the change in height, as we factor that out, delta h. And what is that? That gives us the work being equal to the change in potential energy. What about doing the work to stretch a spring? Well, we're going to start again with work is equal to the integral of f dx. And if we're stretching a spring, then we know that is going to be fs. So we have work is equal to the integral of kx dx. But this k is a constant, so we can pull that out. So that becomes the integral of x dx, and that's going to be from x initial to x final. And we know that the integral of x dx is 1/2 x squared, so we can say that's going to be 1/2 kx squared from x naught to x final, or we can say 1/2 kx final squared minus 1/2 kx initial squared. So what's the change in this? This is the change in spring potential energy. Just reviewing this idea of area, if we have a changing force, no matter what that happens to be, we know that the work is the area underneath the curve. But just be careful, because if we have work above the x-axis, this is going to be positive work, and work below the x-axis would be negative work. So no matter how we set this up, if we had a curve like this area, which is the integral, is going to be added with this negative area to find the net work. Just reviewing this idea from before, we know that average power is equal to work over time. But what if the power is changing and we want to find the instantaneous power? Well, the instantaneous power would be work over time at that point. And what would that be? That would be the slope of the line. Well, taking the derivative, we would say that derivative of work and this derivative of time would give us the slope of the line, which would be the instantaneous power. So instantaneous power is equal to dw over dt. Now, I've seen this question come up before where they ask you about the unit for work, broken down into fundamental units. So we know that a watt is the unit of power, and that's a joule per second. Well, what's a joule? A joule is a kilogram meter squared per second squared. But we're dividing that by seconds. So multiplying through by 1 over s and 1 over s, these will cancel. That becomes s cubed. So that becomes a kilogram meter squared over second cubed. And what is that? That is a watt in fundamental units. So let's look at an example where we actually have a force that is changing. So let's just say we have a function, and that function is minus x squared plus 6x minus 4. So this is what the force is doing. It's not constant. Well, if we graph that, that will give us a parabola. And we have an f, and that graph will look something like this. And let's say we do this from 1 meter to 5 meters. And the question is, what's the work? Well, the work is going to be equal to the area. And how do we get the area under a curve? Well, we do the integral. So that's going to be f dx. So we're going to integrate, and that's going to be the integral of minus x squared plus 6x minus 4. And we're going to do that from x naught to x final. So what do? We perform our integral, and our integral here is going to give us minus x cubed over 3, and the integral of 6x is going to become 3x squared, and our minus 4 is going to become minus 4x. So how would we do this? If we're doing it from 1 to 5, then we would say 1 meter to 5 meters. And then we would set this up with all of our values. So that would become minus 5/3, and the 5 is cubed, plus 3 times 5 squared, minus 4 times 5. So all of that is our final, minus our initial, which is going to be minus 1 cubed over 3, plus 3 times 1 squared, minus 4 times 1. And if you do the math on that, you end up with 98 joules, and that is equal to the area under this curve. This starts to get into some stuff where they ask you very tricky questions that have to do with some of the nuances of these definitions. So we did mention this in one of the earlier videos, but we're going to go over it again. What is a conservative force? In conservative forces, you end up getting your energy back. In other words, there's no losses to heat. But the problem with conservative forces is that the force is opposite the direction of the displacement. So, for example, springs, when we stretch out a spring, the force is opposite the direction of the displacement. And the same thing with the force of gravity. If we are to lift something, it gains potential energy by going up, but that change is negative because the force of gravity is down, opposite that displacement. So we can say that the work done by conservative forces, spring forces and the force of gravity, that gives us a negative change in potential energy. And this is very, very important. So we're going to say conservative work is equal to the negative change in potential energy. This is a definition. And why is this? This is because the force is opposite the displacement. So another thing that you need to know is that conservative forces produce energy, and that energy is not path dependent. In other words, as long as we look at the initial start position and the final start and the final finish position and the height that that experiences, it doesn't matter if the mass traveled some wacky path to get up there. When it gets up here, no matter which way it took to get there, whether it went straight up or over here, or it went up and back down, at the end of the day, the energy change is equal to the difference with this height. But remember, it's negative. Why is it negative? Because the force of gravity is opposite the displacement, so our conservative work is equal to negative delta U, using U for potential energy. And it's the same for springs. When I stretch out a spring in this direction, the force is opposite the displacement, so we say W is equal to negative Fsx, which means our conservative work that's done is equal to negative W, negative U. So we can write this as an integral as U is equal to the integral of negative f dx. x. So before we were writing this as work is equal to the integral of f dx. But when it's potential energy, we need to put a negative sign in there. And that's when we're moving this from x naught to x final. So what's the reverse of an integral? The reverse of an integral would be a derivative. So we can flip this around, and instead of saying that u is equal to negative f dx, what's the opposite of that? We can take the derivative of u with respect to x, du dx, and we need our negative sign in there to find the force. So let's do a couple of examples of this so you can see how this works. Our example would be for gravity lifting an object. So we can find the force by taking the derivative of the potential energy. So we say the force is equal to negative mgh over dx. In this case, that would be a dh. And then we take our derivative, and what does our force become? Our force of gravity becomes negative mg. And that makes sense because the force of gravity is acting down. Another example we could do is the example of a spring. So we can say, again, F is equal to negative du over dx. And we know that the potential energy of that is going to be minus 1/2 kx squared over dx. And if we take the first derivative, that gives us the force of the spring is equal to minus kx, which is what we would expect. So all of the springs that we have talked about up until now have been Hooke's law springs. That is, that Fs is equal to some constant times x. So in these types of springs, the force of the spring is directly proportional to x. That's our linear relationship. So if we were to graph this Fs and x, the slope of the line would be k, and that would be a constant. But not all springs obey this law, Hooke's law. Some springs change where the force itself is changing as x changes. So an example of this would be saying, let's say we have a force of spring that's equal to negative kx cubed. And let's say they want us to find the spring potential energy when it's stretched some distance, let's say, we'll just call it x, so from 0 to x. So how do we do that? Well, we know that the formula for potential energy, because it's a conservative force, is going to be negative f dx. That's our force of spring. So we take the integral of minus 2 kx cubed dx, and we can bring our 2k out, and we have two negative signs, so that becomes positive. So that's 2k, the integral of x cubed dx from 0 to x, and that's going to give us, when we perform the integral, 1/2 kx to the fourth. These questions frequently show up as a multiple choice question, but occasionally they do end up as a free response. So this is a Richard White problem that I found online, and he has many PDFs that you can find of sample problems, including their solutions. So let's go ahead and see if we can solve this problem here. We have a conservative force that acts in the x direction on a particle of mass 2 kilograms to produce a potential energy curve above. So here's our potential energy curve as it's changing. And it says the particle is released from rest at 0.5 meters. So at 0.5 meters, it's at rest, so that's going to be approximately 5 joules. So what's the potential energy of the particle at this position? Well, the value would just be 5 joules, and we just read that from the graph. Now, it started at rest, and they didn't ask us this, but we're going to need to understand this later. So the kinetic energy is 0 joules when it is at 5 joules at 0.5 meters. So the next question says, what's the velocity of this particle at 2 meters? So to do this, we're going to compare the initial potential energy and the initial kinetic energy, in other words, the total energy that we start with, to the final potential energy and the final kinetic energy. So what is the initial potential energy? Well, we know that when the kinetic energy is 0, this is 5 joules. So that would be a best place to start because we know what K initial is. So that would just be 5 joules plus 0. And at 5 meters, at 2 meters, so we have to go to 2 meters, that value is -3 joules. So we know that is -3 joules plus 1/2 mv squared, and that m from the problem they gave us was 2 kilograms. So just plugging in the numbers and solving for v, you get 2.8 meters per second. In part 3, it says, describe the point on the u curve at x equals 4 meters. So what happens when the released particle reaches this position? So again, we want to look at the potential energy, actually the total energy, so the potential energy and the kinetic energy, and we'll do this initially at 0.5 meters. And then we can compare that to what it is at 4 meters. So we're really doing the same thing that we did before. So we know at 0.5 meters, it's 0 and 5, so we just have 5 joules, is equal to, and what's the U final at 4 meters? Well, we need to look at our graph. At 4 meters, it is 1 joule. So we can come down here and say that that is 1 joule. So what is the K final? That should have been a final. So what's K final? K final then must be 4 joules. Well, what does that mean? It means that it has kinetic energy. It's moving. So it's moving, but also take a look at this. The slope of the line is 0. So remember that F du dx, the slope of that line is the force. And if the slope of the line is 0, then the force is 0. So what's it doing? Well, it's moving, but it's no longer accelerating because the force is 0, but it does have kinetic energy. Then the final question says, does the released particle reach 7 meters? And if not, explain why. If so, describe the particle's behavior. So we're going to do the same thing that we did before. We are going to say the total energy, Ui plus Uk, is equal to Uf plus Kf. And this time we'll do it for 0.5 meters, and we'll do it for 7 meters. So, like we've done before, we know that this initial energy is 5 joules total. And then at 7 meters, we need to look at the graph. Well, at 7 meters, the energy is 3 joules. So we have 3 joules plus K final. So what is K final? Well, K final must be 2 joules. So the object is still moving to the right, but again, take a look at this. The slope is 0. So if the slope is 0, there's no more force. So the object is just going to continue moving with the same velocity. In part B, it says a second particle, also of mass m, is released from released from rest at x equals 8 meters. So that means its initial velocity is 0. It says describe the behavior of the particle. But look at what's happening at 8 meters. We know that the force is du dx, and the slope of this line is 0. So that means the force is 0. Well, if there's no force on an object at rest, what's it going to do? Well, it's just going to stay at rest. And then the last question says, sketch the graph for the conservative force that produces this energy curve. So the easiest way to sort of find out the shape of it is to look at what's happening on the potential energy graph. So we know that at every turning point, here, 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 and this whole segment right here, that the values have to be 0 because the derivative is 0. So here on this graph, we just end up putting in our points at 0 that line up with those. And then we know that this is the negative. The conservative force is going to be the integral. So the slope is going to give us something very similar to what we had before. And then 0 at the end because there's no force creating any acceleration at the end.